Hello everyone. In this introductory video of thermodynamics, we will learn some important definitions related to thermodynamics. First, let us define the word thermodynamics itself. Thermo means heat or energy, and dynamics means transformations. Therefore, thermodynamics is the study of energy and its transformations from one form to the other. There are different forms of energies such as chemical energy, electrical energy, kinetic, potential, and mechanical energies, etc. And we see various energy transformations from one form to another form in our everyday life. For example, in a hydroelectric power plant, the potential energy of water sitting at an altitude is first converted into kinetic energy of flowing water, which is then converted and stored as electrical energy. And in an internal combustion engine, the energy stored in the chemical bonds of gasoline is first converted into heat energy, which is then converted into mechanical energy that moves the car forward. Thermodynamics is a universal science. That is, the laws of thermodynamics governs everything around us, starting from working of an internal combustion engine to folding and interaction of biological macromolecules such as proteins, RNAs, and DNAs to the expanding universe. We cannot find a system that violates the laws of thermodynamics. In this chapter, we are going to introduce several properties such as internal energy, enthalpy, entropy, Gibbs free energy, and discuss various laws of thermodynamics, that is, zeroth law, first, second, and third laws of thermodynamics. Next definition: thermochemistry. Thermochemistry is a branch of thermodynamics, and it is the study of the heat energy absorbed or released during chemical reaction and or a physical transformation. For example, let us take a look at the following chemical reaction. Methane gas reacts with oxygen gas to form carbon dioxide and water. This is an example of a combustion reaction. And in any combustion reaction, heat is released. That is, heat is on the product side of the reaction. This reaction is used in cooking or heating homes in many cold countries. Next, let us consider a physical transformation in which a piece of ice melts into water at room temperature. In this reaction, the heat is absorbed. That is, heat is on the reactant side of the reaction. To discuss the energy changes involved in such reactions and to visualize the direction of energy flow or heat flow, scientists often divide the entire universe into two parts: system and surroundings. System is the part of universe that is being analyzed or observed. Surroundings is the remaining part of the universe, that is, everything else except for the system. The system and the surroundings together form the universe. Let us now go back to the two examples that we discussed and identify the system and surroundings in them. In the reaction 1, the reactants and products of the reaction are the system, that is, methane, oxygen, carbon dioxide, and water constitutes the system. Everything else in the universe, except the reactants and products, is surroundings. In this case, the container in which the reaction is occurring, the room in which the reaction container is placed, and everything else constitutes surroundings. In this reaction, energy in the form of heat flows from the system to the surroundings. Such type of reactions are called exothermic reactions. In the example 2, the reactants and products of the reaction, that is ice and water, constitutes the system. The container in which the process is occurring, the room, the air, and everything else except for the reactants and products is surroundings. In this reaction, the heat energy flows into the system from the surroundings. These type of reactions are called as endothermic reactions. A common type of system that we discuss in thermodynamics is a sample of ideal gas taken inside a rigid cylinder with a movable piston as shown in the figure. In this case, the ideal gas sample is the system, and the cylinder, air, and the room around the cylinder constitute surroundings. Depending on the flow of matter and energy between the system and surroundings, systems can be classified into 3 different types: a closed system, an open system, and an isolated system. Let us discuss what each of these systems mean. In a closed system, the exchange of matter between the system and surroundings is not allowed. That is, matter does not come in or go out of the system. Now, the question is, how can you restrict the movement of matter between the system and the surroundings? Simple answer: we can seal the container in which the system is there. Since the exchange of matter is not allowed between the system and surroundings, the mass of a closed system remains constant over time. In a closed system, the exchange of energy is still possible between the system and surroundings. Now, the question is, how can we restrict the movement of matter while allowing the movement of energy between the system and surroundings? The answer is, the walls of the container are made of conducting material such as iron, copper, aluminum, etc. An example of a closed system is a chemical reaction happening inside a closed vessel made of conducting material such as iron or copper. Next, let us discuss what an open system is. In an open system, both the matter and energy can flow between the system and surroundings. An example of an open system is a chemical reaction happening inside an open vessel and made of conducting material such as iron. Since the exchange of matter is allowed between the system and surroundings, the mass of a closed system may change over time. Another example of open system is human body. We exchange both heat as well as matter between the surroundings and human body. Third, isolated system. In an isolated system, both the matter and energy cannot flow between the system and surroundings. An example of an isolated system is a reaction happening inside a closed vessel made of insulating material such as a thermos flask. Let us now look at some of the properties of a system. Let us take an example of a sample of ideal gas inside a container. We can define some properties of the system as pressure, volume, temperature, etc. And we are going to introduce some more properties of a system later in this chapter. All these properties of a system can be divided into two types: extensive properties and intensive properties. First, extensive properties. The properties of a system that depend on the amount of the system are called extensive properties. For example, the mass of the ideal gas sample is an extensive property. The mass of ideal gas sample depends on the amount of the ideal gas. If we take 1 mole of ideal gas, if it weighs x grams, then 2 moles of ideal gas weighs 2x grams. Therefore, mass depends on the amount of the ideal gas. Therefore, it is an extensive property. Some other examples of extensive properties are volume, internal energy, enthalpy, entropy, Gibbs free energy, etc. The extensive properties are additive in nature. That is, if we break a system into two parts, for any extensive property, the property of part 1 of the system plus the property of part 2 of the system gives the total property of the system. For example, if we take a sample of ideal gas, break it down into two imaginary parts, volume of the part 1 plus volume of the part 2 gives the total volume of the system. This equation is only applicable for extensive properties. Next, let us discuss what an intensive property is. Intensive properties, on the other hand, does not depend on the amount of the substance. For example, the density of an ideal gas is an intensive property. As you increase the amount of ideal gas, its mass increases and its volume also increases, assuming the pressure and temperature are kept constant. However, the density of the ideal gas, which is mass over volume, does not change as you increase the amount of the substance. Therefore, the density is an intensive property. Some of the examples of intensive properties are temperature, pressure, molar specific heat, etc. Intensive properties are not additive. Let us take a look at the same example. If we take a sample of ideal gas in a cylinder and divide it into two equal parts, the temperature of one part of the gas is the same as the temperature of overall gas sample. And you cannot get the temperature of the total gas by adding the temperature of part 1 and the temperature of part 2.